All right, so let's go ahead and start chapter 4. This chapter is all about systems of linear equations that we'll be solving using 3 different methods. So these 3 sections are just going through different methods of solving systems of linear equations. You don't have to use one over the other unless the question explicitly tells you to. Some are easier than others though, and we're going to start off with graphing, which is the one that's a little bit longer. But it kind of shows you what we're looking for when we're solving systems of linear equations. So let's start off with a definition of what a system of linear equations is. So a system of linear equations, and remember linear equations are what we've been looking at. So it's these equations with x and y in them. Another name for this is a linear system. So if you go further into math, you'll see that you can have systems that aren't necessarily linear. You might have quadratic systems or something with like an x squared, but not just an x and a y. So a system of linear equations consists of 2 or more linear equations with the same variables. And so these are all going to have an x or a y or both. And remember, even if you don't see an x or y, it could just have a 0 in front of it. So we're assuming it's either going to have an x or y or both. There's not going to be any z's or anything like that. And so what these are going to look like are something like this. Usually we'll put curly brackets around it. You don't always see that. But we could have something like 2x plus 3y equals 4 and x minus 5y equals 10. So this is an example of a system of linear equations. Pretty standard. We have an x and a y in both, and they're usually in standard form, which means the x and y on the left, constant on the right. Another example would be something like this. X minus y equals 1 and y equals 3. So this one we still have 2 linear equations. Remember, y equals 3 is a horizontal line, so it's still linear. And this one works because we technically have 0x plus y equals 3. So we do still have the x, we just don't need to write it because it's multiplied by 0. And so when we're solving these, the solution of a system, and this is why graphing is a good method to look at first, because you can really see why we're checking or solving in the specific way. It's the ordered pair, so a point on a graph that makes both equations true. And so we need to see how we can figure this out from a graph. And then the other methods are a lot different, but those ones are going to be a little bit more efficient. This one's just good for seeing why we're doing what we're doing. So let's go ahead and look at some examples. Before we get into actually solving them, let's look at some examples where we're just trying to figure out if a certain point is a solution. So we want to determine whether the ordered pair is a solution to the system. And so we've seen these before. Well, we've seen something similar. We've seen the case where we're checking if an ordered pair is a solution to an equation. And so the difference here is that, remember, the solution of a system is the ordered pair that makes both equations true. So that's the key word there. We want the ordered pair to be a solution to both equations. If it's only a solution to one of them, then it's not a solution to the system as a whole. It's only a solution to an equation. So let's look at the first one here. We're given the ordered pair 2, 5. And we want to see if it's a solution to the system 3x minus 2y equals -4, and 5x plus y equals 15. And so the big thing here is that we need to check it in both equations. And if it's a solution to both, then it is a solution to the system. So let's go ahead and try plugging it into our first equation here, this 3x minus 2y equals -4. So remember, we're plugging in our x and our y. X is 2, y is 5, and we'll plug them in and see if the left side equals the right side. So 3x, so 3 times 2 minus 2 times y, which is 5, equals -4. And let's just start simplifying. So 3 times 2 is 6, minus 2 times 5 is 10, equals -4. 6 minus 10, we can add the opposite, and we get -4, which equals -4. So I'm just putting a check mark here. I'm not writing our answer yet because we don't know if it's a solution to both. So let's go ahead and check it in the second equation. So 5x plus y equals 15. So 5 times x, so 5 times 2 plus y, which is 5, equals 15. 5 times 2 is 10, plus 5, and 10 plus 5 does give us 15. So we have a solution to the first one and a solution to the second one, which means yes, this is a solution to the system. So you always want to make sure you put that final yes or no answer, or say it is a solution to the system or it is not. Because just writing this right here doesn't actually give a final answer. All right, let's try another one. And now that you've seen the first one, I would definitely try to pause and try to do this one yourself. Then you can skip through my work if you want to. So we're given the point 1, -2, and our system is x minus 3y equals 7, and 4x plus y equals 5. So again, we want to plug it in, simplify down, see if the left side equals the right side for both equations. Let's start with x minus 3y equals 7. So x is 1 minus 3 times y is -2 equals 7. Bring down this 1 minus 3 times -2 is -6. Remember, you can multiply those, or you can multiply -3 times -2, which gives you a +6, because we're actually going to be adding the opposite here. So 1 plus 6 equals 7. So we get 7 equals 7. So it's a solution to the first one. We don't know yet if it's a solution to the second one. So let's go ahead and try 4x plus y equals 5. And if you test it in this first equation and it's not a solution, you can stop right there, because if it's not a solution to the first one, there's no way that it's a solution to the system, because it has to be a solution to both. So it's just kind of a shortcut when you're going through these. But this one, it is a solution, so we need to check the second equation. So 4 times 1 plus -2, or you can put -2, equals 5. 4 times 1 is 4, plus -2 equals 5. But 4 plus -2 is 2, which does not equal 5. So since it's a solution to one but not the other, then we'll say no, it is not a solution to the system. All right, so we're trying to find a point that is a solution to both equations, which means that it has to be a point that occurs on both lines if we were looking at this graphically. So let's go ahead and write out the steps for solving by graphing, solving systems by graphing. And if you don't feel comfortable with graphing yet, definitely get a little bit more practice in before you do this homework, because if you can't graph, it's going to make solving systems by graphing really difficult. Because the first step is we want to go ahead and graph both equations on the same coordinate plane. And we're graphing, and again, I don't have graph paper on this, so it might be a little bit messier for me. If you have graph paper, definitely use it, especially for these, because you want to see, well, this will be the second step I write out in a second, but we're looking for where the lines intersect. And if your graph is a little off, it's kind of hard to see exactly where it is, so you have to estimate. But if you're on MyMathLab doing the homework, you can definitely see where the lines intersect because they have the nice coordinate plane set up for you. So that second step is find where the lines intersect as an ordered pair. So we want to write down that ordered pair where they intersect. And then this last part isn't something that I'll do in these every time, but you do want to check your solutions just like we check all the others. And so this is where these previous examples we did come into play. You're just going to plug that ordered pair, or plug the point, into both equations. And as long as you didn't have to estimate, you should get true statements. When you have to estimate, if it's like at a half mark or a quarter mark and you can't tell, those are the ones that are a little bit harder to check because you won't necessarily get a true statement, but you still should get something close to a true statement. All right, so let's go ahead and look at our first example here. I'm gonna go ahead and do this on a new page so we have plenty of room. So examples, solve by graphing. So you'll notice later you might just see solve the system, which means you can use graphing or the other two methods. Normally you don't pick graphing because it takes longer and it's less accurate. But I mean, if you really like graphing, you can. Some of the questions will say solve by substitution or elimination, which is the methods we'll see next. So if it says that, and then you have to solve by substitution or elimination. All right, so number one here, let's look at the system 5x minus 3y equals 9. And I'm going to write these next to each other. X plus 2y equals 7. So for this one, it's not written the same format, so we don't have the equation on top and bottom with the curly bracket off to the side, but we're still given two linear equations, so it's still a linear system. So first thing we want to do here so that we can graph is get both of these into the y equals mx plus b form, so we don't have to plug in points. So I'm going to go ahead and do that on both of these. So on the left side, I'll subtract 5x. So we get negative 3y equals negative 5x plus 9. And I'm going to go a little bit faster through solving for y on these now and graphing them. If you need more practice with graphing and putting into slope-intercept form, go back to chapter 3, get some practice with that homework. We'll move through this part a little bit faster though. And now I'll divide every single term by negative 3. So we get y equals negative over negative is a positive 5/3 x. Remember, leave as an improper fraction. 9 divided by negative 3 is negative 3. And then we'll go ahead and do it with our second equation. So I'll subtract x. We get 2y equals negative x plus 7. Divide every single term by 2. So we get y equals, and again, be careful on this one. This negative x is a negative 1x over 2, so negative 1 over 2. And try to get in the habit of putting the negative on the top or the bottom, one or the other, and it's going to make your graphing with your slope a little bit easier. Plus 7 over 2, and you can leave this one as 7 over 2, but it's not our slope, so we don't need to have it as an improper fraction. So I'm actually going to change it to a mixed number because it's going to be our y-intercept. So we want to see exactly where that's going to be on the graph. So 7 divided by 2 is 3.5. So I'm going to go ahead now and set up our axes. And let's see. Draw these as nicely as possible. All right, so I'm going to do that, and then I'll put our tick marks on there. So we have 1, 2, and if we look at our intercepts right now, one's at 3.5, one's at -3. And their slopes aren't too bad. This one's a 5 over 3, so it'll be going up or down 5. So I'll just go out to 5 or 6 on each. 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And 1, 2, 3, 4, 5. Just roughly 5 or 6 in each direction. So if we look at our two lines, remember this right here is our y-intercept. So we start at -3, and then we're going to go up 5, right 3, because they're both positive. So we go up 1, 2, 3, 4, 5, right 1, 2, 3. And that's pretty spaced out. So I'm going to go ahead and draw our line through there. And try to make it as long as possible because we're going to try to see where these two lines intersect. So as much line as you have is better. So now with our second one, we're going through our y-intercept of 3.5. So we're going to go up 1, 2, 3.5. And now the slope for this one's a little bit harder. So we have -1 over 2. So this means down 1 and then right 2. So if I start at 3.5, we're going to go down 1 and then right 2. Now, if you notice, they line up pretty well with this other. Oops, I think that point went a little bit too low. They line up pretty well with this point right here. And so I'm going to go ahead and just draw our line in right now. And so if you notice, we have the point where they intersect. That is this point right here. And so, like I was saying with graphing, sometimes you'll have to kind of estimate. This one looks like it's at 3, 2. So our solution here, and this part's really important, making sure you're actually writing out the solution, is the point 3, 2. And if we were to check this, this is the actual solution. So if you were to plug this back into both of these equations, you would get a true statement for both. All right, let's try another one. So this next one, we're given 3x minus y equals 4, and 6x minus 2y equals 12. So now with this one, if we go ahead and do the same thing, put them into slope-intercept form, and because we did the last one together, I would try doing this one by yourself. But if not, we can kind of follow through together. So if we go ahead and, oh, I think I wrote down the wrong one. Okay, let me change this one actually. That's going to be one of our special cases that we'll see later. Let's do x plus y equals 4. This one's a little bit nicer to graph anyway. And 2x minus y equals -1. All right, so now for this one, we want to go ahead and get the y by itself. So let's subtract x. This one's nice, we're already done. So we get y equals negative x plus 4, negative x plus 4. So remember our slope here is going to be -1, and we can put that over 1. And now our second line, let's subtract 2x. So we get negative y equals negative 2x minus 1. Divide everything by -1, or just change all of the signs, it's up to you. But we get positive y equals positive 2x and then plus 1. So our slope here is 2 over 1. Now let's set up our axes. And put some tick marks on here. Our y-intercept for this first one is 4. The y-intercept for the second one is 1. So I'm going to go up to 5-ish. 1, 2, 3, 4, 5. We can fit 6, so I'll go to 6. And then I'll go right 1, 2, 3, 4, 5, 6. Left 1, 2, 3, 4, 5, 6. Down 1, 2, 3, 4, 5. All right, and I've been forgetting to label my axes, X and Y. That's just kind of a helpful reminder if you want it there, but you won't get docked, and on my MATLAB exams, you'll already be given an X and a Y there. So not a big issue if you don't write those down. So our first one has a y-intercept of 4, so we'll start at 4 on the y-axis. And then our slope is -1 over 1. So remember, negative on the top or the bottom, not both. So this means go down 1, right 1. So if we go down 1, right 1, I'll go again, down 1, right 1, and let's do one more. We're already getting off, but down 1, right 1, and I'll just go down to the x-axis. The longer the lines, the better, so you can see exactly where they're intersecting. And I'll go ahead and draw our line through those 2 points. You can see just kind of based on how accurately I drew these, I'm going to fix these points. But it was a little bit off with graph paper. You shouldn't have that problem at all. And now let's go ahead and do our other one. So our y-intercept here is 1. And our slope is 2 over 1. So up 2, right 1. So up 1, 2, right 1. We have another nice point where they intersect. If I were to go up 2, right 1 again, have that point there and draw our line through those 3 points. So we have our line here, and we can see exactly where these 2 lines intersect. This is the point 1, 3. So our solution, and I'm writing solution here just so you guys know that this is the solution. You don't have to actually write solution, you could just write the point and then box the point. But again, that's the actual solution, so if you wanted to check it, it would be a solution to both of the lines that we started with. All right, let's try 2 more, and these are 2 of our special cases. So if I go ahead and write out our system, we've got 3x minus y equals 4, and 6x minus 2y equals 12. So if I go ahead and solve for y on both, I'm going to subtract 3x, and we get negative y equals negative 3x plus 4. And divide everything by -1, or just change all the signs. We get positive y equals positive 3x, and then a -4. And now on our second equation, let's subtract 6x. So we get -2y equals negative 6x plus 12. And divide everything by negative 2. So we get y equals positive 3x and then minus 6. So if there's one thing you should notice about these lines, it's that the slope is exactly the same. And if you think back to what we talked about in chapter 3, that means something specific for these lines. So try to remember what that means. We have a different y-intercept. So let's go ahead and graph both of these. Oops. And our tick marks, negative 6 on this one, negative 4 on this one. So I'll go down to negative 6. They both have positive slopes, so they'll be going up. So I don't have to worry about going down more than negative 6. So 1, 2, 3, 4, 5, 6. And then I'll go right 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Up 1, 2, 3, 4, 5, 6, just so they match. Whoops, that was negative 5. All right, so now let's go ahead and graph. So our first one has a y-intercept of negative 4. So we'll start down at negative 4, and our slope is 3 over 1. So up 3, right 1. So we go up 1, 2, 3, right 1. I'll go one more time. So up 1, 2, 3, right 1. And I'll draw our line through those points. Oh, it's not wanting to go. I'm just gonna erase that guy. Okay, let's try this one more time. There we go. All right, so we're going through those 3 points. Now let's try it with the other one. So our y-intercept is negative 6. And our slope is, again, 3 over 1. So we're going to go up 3, right 1. So up 1, 2, 3, right 1. And then let's go one more time. Let's go up 1, 2, 3, right 1. And again, it's a little inaccurate because we're doing it without graph paper on here. But if we go through those 3 points, if you notice, there's no intersection. And if we were to extend this even more, we're still not going to have an intersection of these 2 lines because they have the same slope, which means they are parallel lines. So, because we have parallel lines, this means that we have no solution. There's no intersection, which means no solution. Just like regular equations, you can have no solution. You can have an infinite number of solutions, which is going to be our next one here. So let's go ahead and try number 4. And so we have x minus 3y equals negative 2, and 2x minus 6y equals negative 4. So let's go ahead and solve for y on both of these. I'll subtract x. So we get negative 3y equals negative x minus 2. And divide every single term by negative 3. So we get y equals, again, be careful here, negative 1x. Negative over a negative is a positive 1/3 x. Again, negative over a negative is a positive. And this one's just 2/3, so plus 2/3. It's going to be a little bit of a weird one to graph, but if we go ahead and look at the second one here, subtract 2x from both sides, and we get negative 6y equals negative 2x minus 4. Divide every single term by negative 6. And we get y equals, now here we have negative 2 over negative 6. Negative over a negative is a positive. and 2 over 6 reduces to 1/3 x, and negative over negative is a positive. 4 over 6 reduces to 2/3. So if you notice, both of our equations are exactly the same. So I am going to go ahead and graph this one so that you can see what it looks like to graph one of these with these kind of ugly fractions. So let me set up our coordinate plane here. And if you do see one like this, one of these kind of special cases, you will still have to graph. Even though for this one, it's a little silly because we have the exact same equation, so we're going to be graphing one line. But if we go ahead, our y-intercept is 2/3, which means it's not even at 1. I'm going to go ahead and go out to about 4 on either or on both axes. So 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. And 1, 2, 3, 4. So our y-intercept is 2/3. That's going to be 2/3 of the way to 1. Don't mix this up with slope. We don't go up 2 over 3. So it's 2/3 of the way there, and then we want to go up 1, right 3. So up 1 is 2/3 of the way to 2, and then right 3 is 1, 2, 3, roughly right there. And I'll draw our line through those. All right, so we have our line, goes through 2/3, has a slope of 1/3, and our second equation is exactly the same. So if you imagine kind of graphing this out again, you'd have the exact same line just laying on top of this one. And so since we have those two lines with the exact same equation directly on top of each other on this graph, we have the same line, which means they're always touching. And so we have infinitely many solutions because there isn't a single point where they're not touching. And another way of thinking about this one, let me just add this into number 3. No solution can also be written as the empty set. And infinitely many solutions, the way you'll see it in the homework is they're going to give one equation as the solution, because the solution is all of the points along this line. And so usually you'll use the one that's a little bit more reduced down. So I'm going to say that our solution is x minus 3y equals -2. So on the homework, you'll see either one solution, which you'll type in, no solution, which will look like this, or an infinite number of solutions, which will have one of the equations next to it. All right, so let's kind of summarize all the different solutions we've had. So types of solutions. And this is just kind of big picture what we're looking at. So the first case, and I'm just going to roughly sketch out some XY plane. If we have two lines, we'll say this line going here, this line going down here. If they don't have the same slope, then we're going to have one point of intersection. So we'll have one solution. And with one solution, we say that the system as a whole is consistent. And this vocab doesn't come up a ton, but you might see it in the homework. So just kind of write these down. And then the equations, as a pair of equations, are independent. So they don't depend on each other. The second type of solution we had was when we had parallel lines. And so with parallel lines, we had no solution because they never intersected. And so for this one, we say that the system is inconsistent. So the way I remember this is inconsistent, no solution. If it has a solution, it's always consistent. And then the equations are still independent. And so just think, if they're not the exact same line, they're going to be independent. But if we have this last case here with our XY plane, where we graphed it and we ended up with the same line, we had an infinite number of solutions, or infinitely many. As long as you have kind of the word infinite in there, we know there's an infinite number of solutions. And so for this one, we say the system is consistent because it has at least one solution. And the equations, because they're right on top of each other, we're gonna say that the equations are dependent. So they're the exact same line, so they depend on each other, they are dependent. Okay, so our last little part of the section here is determining the type of solution, so either one, none, or an infinite number, without actually graphing. So let's go ahead and just look at a couple of these examples. We're told to describe each system. So we're going to say what type of lines we have, and then we're going to state the number of solutions. All right, number one, we're given 2x minus 3y equals 5. And I'm going to write them next to each other because we're going to be rearranging these. 3y equals 2x minus 7. So this one we're not given in standard form. Perfectly fine though, it actually helps us because we have less things to move around. But in order to solve these without having to graph them, we want to know what kind of lines we have. So in this first case here with one solution, this means we have different slopes, so they're going to intersect. So if we look at their slopes and they're different, we have to have one solution. If we have the same slope, but a different y-intercept, that means we have parallel lines. And if our equations are exactly the same, that means we have an infinite number of solutions. So let's go ahead and solve for y on both of these. First one, I'll subtract 2x. And we get negative 3y equals negative 2x plus 5. And divide both sides by negative 3. So we get y equals negative over negative is a positive 2/3 x. And then 5 over negative 3 is a negative 5/3. So our slope here is 2/3. And then if we look at the second one here, we go ahead and divide both sides by 3. We get y equals 2/3 x minus 7/3. So again, our slope is 2/3. So once you narrow it down to having the same slope, we can't have this first case. So we either have parallel lines or we have the same line. Since our y-intercept here is different, we can't have the exact same line. So we have to have parallel lines. So this is how we are describing the system. And parallel lines means they never intersect, which means we have no solution. All right, let's try another one. We'll just do 2 more to see what we're looking for in each of these cases. Number 2, we're given negative x plus 3y equals 2. And 2x minus 6y equals negative 4. So let's go ahead and solve for y on both of these. This first one will add x to both sides. So we get 3y equals positive x plus 2. Divide everything by 3. So we get y equals 1x over 3, so 1/3 x plus 2/3. Same as that other example that we looked at in the previous ones we were graphing. Second equation here, I'll subtract 2x. And we get negative 6y equals negative 2x minus 4. Divide everything by negative 6. And we get y equals negative over negative is a positive. 2 over 6 is 1/3 x. And then again, positive 2/3. So with this one, we have the exact same equations, which means if we go back to our graphs over here, same equations means we have the same line. And the same line means that we have an infinite number of solutions. That one's usually the easiest to see. If you have the same slope, different y-intercepts, has to be parallel. And then our last case, this is what we're going to be looking for. So number 3, 6x plus y equals 3, and 2x minus y equals negative 11. So if we go ahead and subtract 6x on this first one, we get y equals negative 6x plus 3. And we're done already. Second one, we're going to subtract 2x. And we get negative y equals negative 2x minus 11. And change all the signs or divide by negative 1. So we get y equals positive 2x, positive 11, so plus 11. And if you notice on these two, our slopes are different. So we can't have the same line, we can't have parallel lines, which means that we have to have one solution. Because if we go back here, this has the same slope, this one has the same slope. The only one that doesn't is when we have two lines that intersect. So we have to have one solution. So we have that they are neither parallel nor the same line, or we can say that they're intersecting at one point, which means that we have one solution. All right, so now we're going to take all of this that we've seen with solving these by graphing, use the same idea to use some, or to see some different methods that are a little bit faster. But remember, we're looking for the point where the two lines intersect. That's going to be a solution to both equations. So we'll see that a little bit more in 4.2.